Hello everyone. My last video where I tested whether we could 3D print a pressure vessel and tested it to failure proved to be quite the success. So I've decided to double up on the concept and shoot a sequel. This time around, we're going to test some new materials. Besides just regular ABS, we're also going to look at carbon fiber reinforced ABS, which is a very popular filament, and even some fiberglass reinforced ABS. In addition to new materials, we're also going to tweak the design a bit. In our first video, we designed to a 1.2 millimeter thick wall, and the nominal pressure rating was around 100 pounds to failure, or at least that was the design case. We're going to stick with those 1.2 millimeter walls, but we're going to make some adjustments to the design and to the slicer settings to see if we can squeeze a little bit more out of those thin walls. So let's get to it. In the spirit of getting as much as possible out of a pressure vessel with only 3 perimeter walls, the first thing we're going to do is get rid of the shell segment. As was pointed out by Ascendant Gamer Sage in the last video, a spherical tank is more suitable for higher pressure than the bullet style tank that is a regular shell with hemispherical heads, which I used in the last video. So that eliminates this entire calculation of hoop stress here. It becomes irrelevant. And the only thing that remains relevant is the hemispherical head stress. The next thing we're going to do is max out the material. In our first proof of concept pressure vessel test, we used generic ABS, which was then vapor smooth to make it gas tight and, of course, as we found out, much stronger than the manufacturer's specifications suggested. So this time we're going to print it out of fiberglass reinforced ABS. And before someone asks the inevitable question, why not use carbon fiber? I do actually have carbon fiber ABS, and in fact it's one of my favorite filaments to print structural parts in. But glass fiber ABS, at least the material I have, is actually quite a bit stronger than carbon fiber. I'm not entirely sure why this is. Carbon fiber on paper should be stronger, but in the context of 3D printing filaments, maybe they're able to get more glass fiber into the plastic before it starts, having effects on the print quality and filament quality, or maybe there's some other interlayer bonding issue at stake here that affects this. But from the spec sheets from existing filament manufacturers, the glass fiber has a significantly higher tensile strength on the actual final 3D printed part than the carbon fiber ABS filaments that I've seen thus far. So we will use glass fiber instead of carbon fiber for that reason. Now, unfortunately, even though the tensile strength data on glass fiber looks very favorable, I don't actually have tensile strength data for the XY axis versus the Z axis. All the testing is done in the X and Y axis. So I'm going to have to speculate slightly here, or do some sort of educated guess as to what the actual XY or what the actual Z-axis tensile strength would be for these glass fiber or carbon fiber filaments, because as far as I know, they haven't actually tested that and given a real experimental value. So that's kind of what we've done here. Again, as before, I did all the calculation iterations in advance. So I did two different approaches here. As usual, the vessel has not changed in size, although we limited the shell. It's now a spherical tank, but the wall thickness of 1.2 millimeters is the same. The the strength of the filament now becomes the big question. And again, what matters here is going to be that z-axis, because the weak spot would be the side, if you will, because we're printing this in a up and down orientation along the z-axis, but the side of the sphere, of the pressure vessel, is going to be the weak point and where it's likely to fail, and that is where the z-axis tensile strength comes in. So the question is, what should that z-axis tensile strength be? So what I did over here was to basically initially assume that the difference in the xy axis to the z-axis strength would be the same ratio that we saw in the ABS actual test data, which gives you a starting value of 37.6 MPa, and that's of course over here. However, a lot of the benefit you see from the ABS going from, say, 21.9 to 68 is coming from the glass fibers, not from the ABS itself. And in the z-axis, we don't have the glass fibers really moving between layer lines because we're extruding one Z layer at a time. And so I don't think you're going to see the full benefit here. You know, you might get a little bit of glass fiber that's in contact with, you know, both layers, but it's definitely not going to have the same effect and the same strength in the z-axis as it will in the xy. So I don't think to give this the same ratio is probably optimistic, because you don't have any fibers going from the xy axis through the z-axis. So I've kind of split the difference here between, you know, the ABS z-axis strength and this assumed. Basically, I'm saying the benefit or the gain in strength will be somewhere between what you see in regular ABS and what you would optimistically assume for glass fiber. So I've got two numbers here. This is obviously, you know, it's basically a heuristic value. There's no data behind this because we don't have data, but it's going to give me two different numbers. So repeating the working pressure and tensile strength pressure rating calculations here, we get a couple numbers. So your optimistic number here is that the vessel would rupture at around 325 pounds, and your more conservative number is that the vessel would rupture at around 215 pounds. Now, we know from the last test that the regular ABS made it to 250 pounds, so it's likely that this is fairly conservative. I would be very surprised if the reinforced vessel did not make it to 250 pounds like the pure ABS one did. But we're obviously going to see. And if you, again, over here, I've got the 2.5 multiple. If we do assume that we see the same 2.5 times improvement after vapor smoothing, as we saw in that first test, we expected it to fail at around 100 pounds and it made it to 250. If that same multiple were to occur in this glass fiber, you would get a, you know, potential max pressure or failure pressure of 813 pounds in the more optimistic case, and in the less optimistic case, it would rupture somewhere around 537 pounds. So a pretty wide range of where this thing could go. Moving on to the model itself, as you can see, we have turned our bullet-style cylindrical tank with hemispherical heads into a true sphere, or very nearly a true sphere. For reference, here's the original model stacked up right next to our new model. Same diameter, same hemisphere, so we just got rid of the cylindrical shell segment. And we did a couple other tricks here to make this work better and really get the most out of this 3-perimeter model. So the first thing we did here, and you can see that with these two object modifiers that I put on the top and the bottom here, is to turn the layer setting here that you're going to see on infill, which is combine infill every 2 layers, and really put that to work for us. So what this combine infill every 2 layers feature does is, and I set it at 2, but you can really set it at any number you want within reason. But the outer and inner orange lines here are your perimeters. And that inner purple line, or lower down here, white line, is your infill. And so by changing the setting on infill to combine infill every 2 layers, what it does with our 0.15 millimeter layer height is it will lay down 0.15 millimeters of perimeter 2 times, and then lay down a single 0.3 millimeter thick layer of infill. And what that does is it basically makes these 2 perimeter walls and that 1 infill wall be interlocked, like you would see, say, on a brick wall, rather than just being all in one single plane. And that means when this, when the pressure is increased and it's, trying to tear the thing apart, it has to actually physically tear through that middle layer and or the outer layers, because it doesn't have a clear seam at every layer where the whole thing can come apart. It's going to make the walls a lot stronger for a given thickness, because now these 3 layers are effectively interlocked with each other. So that's the first item I did. To make that work, you don't just combine infill every 2 layers. You have to change the perimeter setting to just 1, because if you have more than 1 perimeter, all 3 of these walls will be perimeters and you won't get that interlocking effect. However, we do want much more than 1 perimeter wall, especially at the bottom and at the top, where we've got those overhangs that are going to compromise the wall thickness and wall quality. And so that's where those modifiers came in. So these modifiers here change the infill and perimeters from 1 perimeter, which I've set for the default for the whole model, and 100% infill, which is what gives us what we want in the middle here, to 7 perimeters and 30% infill, which is what we used on the last model for both the skirt and the repad on the brim here. So that's what this little bit of programming, if you will, is doing. The other thing you will inevitably notice is there's a little bulge in the middle here. That's not an accident. As we saw in the last pressure test, the failure point was right where the shell meets the hemispherical head, the bottom head, specifically is the one that blew off last time. And again, there's a reason for that. With a pressure vessel like this, your force is being exerted in all directions equally. However, it's going to be the weakest in the z-axis, because that's where we're printing each layer in. And so the weakest part of this hemisphere, and the place where it's most likely to fail, is going to be right here along the center line of the hemisphere in the z-axis. And so to try to help things along a little bit, I added a 1-layer repad that's concentric here and goes about 2 millimeters high. And of course, we've chamfered the edges so that there's no stress risers there. And the logic there is, is still the most likely place for it to fail is now going to be like somewhere around here or somewhere around here, but that force is no longer being exerted directly on the z-axis anymore. There's a cosine or probably tangent factor going in here, because it's no longer able to pull directly against the z-axis. Some of that force is being, pushing outwards in and against specifically that layer. So this will probably buy us a fair amount of improvement for basically very little extra material. And again, this is all about getting the most out of 3 perimeters, so we're going to cheat as much as we can. So that's our model here. Otherwise, we have the same fitting on top, the same skirt on the bottom, same repad there. And let's go ahead and get this printing. And here are our prints. Let's start with the obvious. We've upgraded our pressure testing rig to a 1,000 pound rated gauge, fittings, and valves. As discussed in the earlier parts of the videos, we went ahead and printed ABS with glass fiber Vapor Smooth, which is right here, and ABS carbon fiber, also Vapor Smooth, which is this one. But we've also had a bit of scope creep. By popular demand, I also printed the new model with the adjusted settings in ABS and then ABS and vapor smoothing. This should be very interesting because comparing the results of these two pressure tests will tell us exactly how much of a difference the vapor smoothing makes, and comparing the vapor smoothed one to our previous test will show how much of a difference the new model and new settings makes compared to the model and settings used in the original video. All four of these pressure vessels were printed on the same printer with the exact same settings. The only thing that was changed was the filament type. And in the case of these two, it's the same filament type, in fact the same filament from the exact same roll. Okay, and here we go with ABS not vapor smooth. Okay, this is vapor smoothed ABS. Okay, this is ABS carbon fiber that's been vapor smoothed. Start with vapor smoothed ABS glass fiber. Here we go. If you recall from the first video, these vessels, as designed in ABS, were intended to fail at about 100 pounds of internal pressure. So our first pressure vessel this round, which was unsmoothed ABS, was pretty close to the mark, failing at about 85 pounds. This was kind of interesting because it failed right at the edge of the repad, which in hindsight is something of a stress riser. It has a sharp edge, although that stress riser was on the outside of the vessel and the pressure is being applied to the inside. So that was kind of a surprising result. I could have chamfered this edge, but I didn't think it mattered, but apparently it does. So that was result number one with the ABS there. The second vessel here is our ABS that's been vapor smoothed, and it failed along the very center there. This was a really interesting result for several reasons.
As expected, with the changes in the model, we did improve the maximum pressure that the vessel can take, but the improvement was pretty minimal, about 20%, going from 250 pounds from the first video to 300 pounds for this one. It does nicely illustrate the value of vapor smoothing because these were printed in the exact same filament, and after vapor smoothing that filament, we improved the amount of pressure it could take by 3.5 times. That makes vapor smoothing a much better return on your investment than, say, simply increasing the wall thickness to achieve the same strength, especially if the part weight or part size matters for your application. The vapor smoothing also seems to have addressed the stress riser failure, which occurred on this one, because obviously we failed along the seam, which is the more expected failure location, or the middle, which is the more expected location. And that's likely because when you vapor smooth, you could get a little bit of flow of the surface material, and it likely filled in the sharp edge in the corner here and reinforced that, making it similar to having chamfer at the model level, and made it less likely to propagate a crack. ABS glass fiber, which is this one, and carbon fiber both failed, again, along that same middle section there, which we anticipated would be the weak point. And the carbon fiber failed at 200 psi, with the glass fiber making it to 212 psi. This was a really interesting result. As I mentioned, I think earlier in the video here, I did see some literature that suggested that adding the fiber filling to the filaments can actually make them weaker in the z-axis. That certainly seems to be the case. Remember, if you recall, our regular ABS made it all the way up to 300 pounds. These failed a full, or approximately, 100 pounds less. Again, one made it to 200 and the other made it to 212. So that's a full third of the internal pressure that these couldn't take and the regular ABS could, which kind of flies in the face of the material spec sheet values, which obviously those are in the XY axis, but it does kind of make you think a little bit on that. The z-axis clearly matters more, at least for this model, and that strength is actually reduced by adding those filler materials, whether they're carbon fiber or glass fiber. Also, it was notable that the glass fiber and carbon fiber performance was substantially similar. I mean, one was 200, one was 212. If you looked at the spec sheets, glass fiber on paper is significantly stronger, but that doesn't seem to materialize, at least in terms of z-axis bonding. So, in general, the new model here failed pretty consistently along the very center of our sphere, which is the largest diameter in the z-axis. That is where we expected it to fail, and that's why we put the little repad belt to try to beef that up a little bit, and in theory force the failure point above it or below it. It's kind of hard to tell from these, but it did to a certain extent migrate. Some of these are definitely on the top lip of the belt, rather than say the middle of it. So I would say we were somewhat successful in mitigating that, but all we did is force the failure point to the edge of where that repad is, and the material is thinner. So we could probably improve this design a little bit further by, say, making the belt wider and potentially a little bit thicker. But given our ABS from the first video was 250 pounds, and all the changes we made to the model and the print only netted us an extra 50 pounds of capacity, we're probably hitting diminishing returns on how much more pressure you're going to get out of a vessel of this type just by tweaking the design and print settings. So what conclusions can we draw from all this? Well, the most obvious one is that Big Filament is ripping you off by selling you carbon fiber reinforced filaments when you should just be using cheap old ABS and vapor smoothing instead. I'm joking. There's actually some very good use cases for carbon fiber and glass fiber filled filaments, but the point here is that simply using carbon fiber or glass fiber filament is not a silver bullet for improving your design. You really need to look at the part that you're making in question, identify, which axis and where on the part the weak point is, and then if it is in the z-axis and you have no way of changing that axis, consider alternative approaches for reinforcing it, like vapor smoothing, for example. On the more basic side, for small parts, and I'm foreshadowing my next video a little bit here, ABS vapor smoothing can significantly increase the strength of a part by several times the design value, and can reduce stress risers caused by sharp corners. Vapor smoothing was originally conceived as a mechanism to improve the aesthetics of 3D printed parts, but from this little set of tests here, it's pretty clear that it offers a lot of value as a tool to increase the strength of a part, in addition to simply making it look better, at least in the case of ABS and acetone. I already have some ideas for a third video, so keep an eye out for that. There were some really good ideas on my last video that contributed to what we did here, so if you come up with any other ones, drop me a comment below. That's all I have for now. Thanks for watching.